Hello, everyone. My name is Alexander Lidiak. Today I'm going to talk about my work with my PA, Zhexuan Gong, at the Colorado School of Mines Physics Department, using diffusion maps to find quantum phase transitions. So the work and extra details can be found here at this archive link. And the PRL is currently in production, which we're excited about. So first of all, why do you need to use machine learning in quantum devices, or why is it helpful? So we are in the NISQ era of quantum computing, and what that stands for is noisy intermediate scale quantum computing era. So quantum implies that you have these Hilbert spaces, local Hilbert spaces that scale exponentially, and to get measurement readouts or projective measurements, you have results in these classical bit strings of zeros and ones here, as shown here. So this is an example of when I say what a sample is, this is an example of what it would be like. So just this classical bit string that is of length your system size. So this results in these large data sets that exist in large state spaces. And you get these large data sets in quantum simulators to determine things like entanglement entropy or quantum gate fidelity, and etc. So these extract nonlinear, so a problem is, how do you extract nonlinear physical features from these large data sets in their large state spaces without a very good a priori understanding? So for example, quantum simulators, you don't fully understand quite well yet. So this is where unsupervised machine learning can come in. So you can extract features of large data sets very well by using machine learning. Not only that, but you can also reduce the dimensionality of the problem. So you can reduce the dimensionality of these large state space data sets to try to understand better what's going on, or maybe see it from a different perspective, which is also valuable. So we're going to talk about the diffusion map method, which is a nonlinear dimensionality reduction method that's very useful. So it's the eigensolutions of a diffusion process in your sample space. So if we have two examples, say XL and XL prime, we can define a transition probability between them that depends on this kernel function and parameter epsilon. So typically you choose a kernel such as the Gaussian kernel, just a kernel that usually depends on your distance between the states or the sample states in sample space. So here we call that R, so that's just your distance between states. And for a qubit system, that's essentially just the number of spins that are different or in different orientations. So then you finally solve for the eigenvalue equation in which you have your probability, your transition probability matrix. You essentially solve for its eigenvalue equation, and you get this set of lambda, and these lambda essentially determine your clusters, and they determine your clusters by the number of lambda that are approximately degenerate and equal to 1. And you can actually control these, essentially which regions are clustered together, by controlling epsilon. And this epsilon is generally proportional to the fraction of the spins that are different out of the total number of spins that can be different for a qubit system. And this essentially just shows you kind of essentially what samples and different distances between the samples will essentially be called clustered, or essentially have a reasonably high enough probability, transition probability, that they will diffuse into each other. And whichever sections of samples are connected by this diffusion process are essentially considered a cluster. So if you expand epsilon, you essentially would have a reasonably high transition probability from these two, and they would likely be considered a single cluster. And that's just a 2D representation of the Gaussian envelope or Gaussian kernel here. Sorry, I'm not sure what happened there. So this actually helps you extract the number of clusters that you get in each of these regions of epsilon actually is very important for determining the physics that's happening. So for very low epsilon, you just have essentially the number of unique samples, and that's because it only is privy to the number of spin flips that's very low, so like 1 or less. So that essentially just determines what samples are unique here. So you don't have any sort of larger clusters that occur. So then when you increase your epsilon to an intermediate region, somewhere between none of the spins are different and half of the spins are different, you start to get more interesting clustering. So for example, in this play model here, you have, once you have these overlapping spheres, you can consider them essentially a cluster because they're likely enough to diffuse into each other and essentially create these sort of mini clusters. And this varies quite a bit for different quantum phases. And that's very interesting because you can actually determine different phases by how they behave differently in this region. And this is the case for many body localization and valence bond states and this Z3 symmetry breaking phase transition we also show later. So, and then finally, when you have a very large number or very large distance, you get these sort of discrete symmetry breaking orders that come out. And this is essentially, so for example, the ferromagnetic case where you have them all up or all down, this will essentially be two very distinct clusters if there were the ferromagnetic case. So moving on for an example, here's the valence bond state. So, sorry, this is the J1, J2 model, and it undergoes a valence bond solid phase transition. So a valence bond state is essentially here that you have this dimer and it adds up to a singlet. So it can either be up and down or down and up. So here's an example of the number of clusters versus epsilon. So here I plot the all of these J2 states except for the middle part, which is here in red. And essentially what happens in this middle point is there's a symmetry breaking that occurs. And the diffusion map method shows that the symmetry broken versus the equal superposition states are clustered in a very, very different way and have a very, very different dependence. And in our paper, we show exactly why that happens. It's interesting. But adding this very small symmetry breaking field so that you have a finite symmetry breaking instead of an infinite lattice symmetry breaking helps you determine exactly where the phase transition is. And the diffusion map method shows that the number of clusters drops drastically around where the phase transition point is predicted at 0.3. As another example, sorry, I don't have time to go into too much detail on the Hamiltonian. This Z3 chiral clock model is a very interesting model to explore. So you have this paramagnetic phase, a ferromagnetic phase, and an incommensurate-like phase, and this is essentially an intermediate between these two. And this is the entanglement entropy, which is the typical indicator of this phase transition. But entanglement entropy is fairly difficult to obtain from experimental data. So here, when you use experimental data and feed it into the diffusion map, it actually fully determines the phase transition fairly well. And it's important to note here that you can also do this not only with sigma measurements, but also tau, which is very interesting and shows the method is somewhat robust. So last but not least, it also returns your discrete symmetry. So here it indicates your Z3 symmetry. It actually has 3, and it shows you the 3 clusters, just like that figure I was showing earlier. So it can also help you determine the exact sort of physics that's that your system is exhibiting. So there's also the many-body localized phase that we explored. So here you have your number of clusters versus epsilon. So for the very small epsilon case where it reflects the number of unique samples, you essentially have that your number of samples goes down as your localization increases, which makes sense. In an intermediate epsilon, you have this peak near the phase, near the many-body localization phase transition. And we believe that occurs because you have this competition of ergodicity in this state and localization in this state that leads to these sort of large number of mini clusters that are separate enough but have enough localization such that they form these little mini clusters, like kind of like we showed in that figure. Kind of like this. So in conclusion, the diffusion map method is a very versatile and highly parallelizable nonlinear machine learning technique that can automatically determine or indicate topological, discrete, valence bond state, and many-body localized phases just from measurement data, which is very useful. So yeah, please check out our paper here. And thank you very much. So thank you to Colorado School of Mines Physics Department, everyone working there, and my advisor, of course, and office mates, etc. Thank you.